Hello dear student, I welcome to our new topic. Our today's topic is intermediate bonding. What is intermediate bonding? You know, we got two major type of chemical bonding in chemistry. One, ionic bonding, when you get a compound formed between a metal and non-metal, and another is covalent bonding. This we get when two non-metal atoms make their bonds. And then intermediate bonding is a bonding between these two. I mean, it's not 100% ionic and not 100% covalent. Maybe the compound consists of 90% ionic and 10% covalency, or this can have 90% covalency with 10% ionic properties. This type of bonding we call intermediate bonding. And we're going to explain the reason for the deviation, how an ionic compound can have some covalency and how a covalent compound may have some ionic character. So let's start with first how a covalent substance have ionic properties. To study ionic properties in covalent substance, we first need to recall what is covalent bond. A covalent bond is formed when two non-metal atoms overlap to each other, they share a pair of electrons, and that forms covalent bond. How we define that? We say that the electrostatic attraction between the shared pair of electrons and nuclei of the atoms. Let's see. Here you consider an atom and here is another atom, and both the atoms put a pair of electrons in the middle and their nucleus together we call nuclei attracting the shared electron. Here you get, because nucleus are positive, so certainly they will attract the shared electron. This is covalent bond. When you make a covalent bond with same atoms, maybe this is a hydrogen atom, this is also a hydrogen atom, then the nucleus will attract the shared electron equally, because both the nucleus are same elements, that means they have same nucleus and the size of the atoms are also same. But if you get a covalent bond with two different atoms, do you think both the nucleus will attract the shared electron equally? Certainly not, because all the atoms have different nuclear charges and different size. Because of the different nuclear charge and different size, they're gonna attract the shared electron unequally. This specific element attract the shared electron differently, and this we call electronegativity. So electronegativity means the attractive power of an atom, its nucleus, for the shared electron. As you know, all the atoms have different nuclear charge and they have different sizes, so certainly they will have different value of electronegativity. Atoms with greater nuclear charge and smaller in size have stronger electronegativity. So we get in periodic table left to right, when you move across the period, we get electronegativity of the elements increases, and this decreases down the group because the size gets bigger and bigger. So if you make a bond with two different atoms, suppose one is hydrogen, another is chlorine, certainly they will have different electronegativity. This time this nucleus will have different attractive force for the shared electron. So what will happen to the shared electron when you make a bond with different atoms? Let's consider one atom is hydrogen with nuclear charge +1, and the other atom is chlorine, nuclear charge +17. So certainly we get +17 is much greater than +1. That means electronegativity of chlorine is much greater than hydrogen. What would happen to the shared electron? Do you think the shared electron will be at the middle of these two atoms? Certainly not, because that's being pulled away by one nucleus greaterly, and this causes a distortion of the position of the shared electron, which means the shared electron will move to the more electronegative atoms. Suppose we get, this is a bond, hydrogen and chlorine. We normally suppose they should be at the middle, electrons should be at the middle, but what happens, the electrons moves to the chlorine atoms, and when this happens, two different atoms bond and shared electron moves to the more electronegative atoms, then the distribution of electrons and electron density will not be same, and this causes formation of slight charge on the atoms. That means the more electronegative atoms will have some negative charge, which we get slightly negative, which is del negative, and the less electronegative element will have slightly positive charge. So here you get, I am giving hydrogen as slightly positive charge and chlorine slightly negative charge. This is because there is unequal electronegativity of the atoms. The more electronegative atoms attracts the shared electron more than the other. So this will cause the shared electron to move to the more electronegative atoms and forming positive and negative poles of the molecules. And look carefully, this is a covalent bond and supposed to be molecule without having charge, but eventually charge develops there. Slightly positive and slightly negative also charges. That means the covalent substances gaining some ionic character. So this is we call intermediate bonding, and this is certainly a covalent bond and is a molecule but has a degree of ionic properties. And then any molecules you get consist of just one bond. If the bond is polar, I mean the shared electron moves to one of the atoms, the molecule is also polar. But this may not happen in molecules with multiple bonds. I am going to show you an example. Here you see a bond between carbon and oxygen. Do you think this bond is polar? Certainly you should think, because here you get oxygen is more electronegative than carbon. So shared electron is supposed to move to the oxygen atoms, forming negative pole on oxygen atoms and positive pole on carbon atoms. So dipoles and then polar molecules. But now we consider this molecule is carbon dioxide. So here another pair of bonds and is another oxygen atoms. Do you think this molecule is polar? No, really not, because here dipoles cancel each other. This happens when both the atoms on both sides pulling the electrons of carbon equally. This we call symmetric. This molecule is symmetric. Symmetric means the central atoms have equal bond angle around and same atoms are bonded on the central atom. This is a symmetric molecule because you get here is bond angle 180 and here is also bond angle 180. So equal bond angle around the central atom, and these two atoms are also same. So symmetric molecules cancel the dipoles. So the molecule overall is not a polar molecule. And I am going to show you some more examples of symmetric molecules. This is one boron trichloride. So boron bonds with 3 chlorine atoms. There's 3 chlorine atoms bonded to the boron. This is boron trichloride. This is also a symmetric molecule. This is because the chlorine atoms, so all 3 are chlorine atoms and bond angles all are equal, which is 120. So this is symmetric molecule and dipoles will not persist there. Dipoles will cancel each other. So normally we can generalize, if a bond is formed with 2 different atoms of different elements, the bond must be polar because one of them is more electronegative than other. So shared electron will move to the more electronegative atoms, causing dipoles. And if we get molecules with just one bond which is polar, the molecule is we also call polar. But we can get some molecules with multiple bonds where maybe if this is symmetric, if the shape is symmetric, the dipoles will cancel each other and overall the molecule may be non-polar. And if this is the case, the molecule is 100% covalent. And whenever you get 2 atoms of same element bond, that is 100% covalent, because this 2 atoms of same element means 2 atoms have same electronegativity. The shared electron will not move to any of the atoms. So that is 100% covalent. Whenever you get the molecules with dipoles, I mean polar molecules, they will have some ionic character, ionic properties. They will be affected by the charge rot and will have greater melting and boiling point. Now we're going to focus on ionic bonding. Ionic bonding, ionic bonding is formed between a metal and non-metal. Here we define ionic bonding as the electrostatic attraction between a cations and anions. Let's draw the simplest one, which we call sodium chloride. Here is sodium and here is chloride, plus minus. These two are oppositely charged ions, so they will attract each other. But this sodium chloride gets little covalency because when the cation sodium here attracts the electrons of anions, the electrons of anions moves slightly towards the cations. This is normal because electrons are like airy, so they can spread out. When the cations pulling the electrons of the anions will slightly move to the cations. So this we can show with this diagram, that electrons are moving slightly towards the cations. Okay, and this movement, this distortion, causing the covalency in ionic substance because their electron density rises between the ions. So the basic difference between covalent bond and ionic bond is, in covalent bond you get greater electron density between these two particles which bond, and in ionic bond we get electron density between these two ions are very poor, very low. But when the cation distorts the electrons of anions, electrons of anions moves towards the cation slightly, that means electron density rises between the ions, which means this develops covalency. Here we use two different terms to explain how covalency develops in ionic compound. One for the cation, another for the anion. For the cation we use polarizing power, which means the cation distorts the electron cloud of anions. Its ability is called polarizing power of the cations. I can show you, this was sodium. If this is magnesium, how do you think the polarizing power of magnesium compared to sodium? Certainly you think this is greater because its charge density is greater, which means the electrons of chloride, this still chloride, will move to the magnesium more than that caused by sodium, which means that this compound, magnesium chloride, will have greater distortion and greater covalency. The amount of covalency also depends on the anions, not only on the cations, not only on the polarizing power. This also depends on the anions. How? If the anion is bigger, consider this was magnesium, I still write magnesium, another magnesium ion, but here I am giving you bromide ion. Do you think this will have the equal distortion? No, certainly not, because bromide is much bigger than chloride, which means here bromide will be distorted more by the magnesium. Here you see greater distortion occurs by magnesium. How we explain this? We say this ability to be distorted by the anions is polarizability. So we say bigger the size of the anions, greater the possibility of distortion by the cations. This ability to be distorted we call polarizability. So when ions, negative ions, are bigger, they have greater polarizability, and which causes greater covalency. None of the ionic compounds we get with 100% ionic properties. At least they have slightly covalency, because this distortion always occurs in any sort of ionic compounds, but this is different in different ionic compounds. Consider one, aluminum chloride. Aluminum is 3+, charge density is very high here. If you give here chloride ion, the distortion will be huge. The distortion basically huge, which means the electron density between these two particles rises up, which causes greater covalency. And eventually we say aluminum chloride is a molecule, which means this is not ionic compound, this is covalent compound, because this has greater covalency than ionic. So this was our intermediate bonding, which means ionic substance have some degree of covalency, and this is different in different ionic compounds. And covalent substance, yes, some covalent substances are 100% covalent, and most of the covalent compounds are not 100% covalent. They got some poles, dipoles, and got some ionic properties. So I think this has made your concept very clear about intermediate bonding, and if you really like our class, stay with us to get more of this type of video to make your chemistry classes much easier. Thank you.